welcome back, everybody. Here's a triangle. Whoa, not yet, but there's going to be. Here's a triangle. And hypothetically, I tell you that that's a right angle, and this is 60 degrees. I'm going to claim that this side length is, I don't know, 8. What's the length of my hypotenuse? Why? You're correct, first of all. You double the short leg to get to your hypotenuse. So this is 16. Love it. What is this one? 8 times root 3. 8 root 3. Okay, I remember this because 3 different angles. 3 is root 3. Cool. In contrast, if instead I gave you a 45, 45, 90, which is an isosceles right triangle. Let's say this side is 12. What's this side? Good. And this side? Two angles are the same. I will use root 2 this time. Now, leg to hypotenuse is multiply. Hypotenuse to leg, you would divide, right? Cool. We are using that to build these 3 triangles, which bow ties and butterflies is the phrase that you're going to hear. Cool. I asked you to finish one little piece of it last night, and you might have found something kind of interesting or not interesting. I don't know. It's kind of opinion-based. I'm going to drop that straight down like we did before, and it gets really ugly if we do it to the whole circle and do this everywhere. You'll notice I also quit writing the angles. We'll do that here in a minute. What's this last ordered pair? What kind of triangle is this? Peach? Is this peach? Okay. What kind of triangle is peach triangle? Where's the 30 this time, though? The top. Now, why did I put a 1 on the hypotenuse? It's the radius. It's our unit circle. It's always going to be 1 here. So let's see. We have a lovely hypotenuse, and I want to get to, let's say, the short leg first. That's this side down here, right? Okay, how do you go from hypotenuse to short leg? Not double. That's short to hypotenuse. You divide by 2, so what is it? This is the order pair 1/2. That's our x value, right? Okay, how about now that we know that the short leg is 1/2, how do we go short to long? So 1/2 times root 3, I'm just going to simplify it out and call that root 3 over 2. If you remember these 2 special triangles, that's the most memorizing that you're ever going to have to do for the unit circle. These 2 special triangles show up everywhere because they're so nice to deal with. Now, there are other ways to memorize the unit circle as well, but I'm going to make a claim that this is all you really need. Now, this requires you to do a little bit of math in that process, which, I mean, it's not a bad thing considering we're in a math class. But I'm going to pass you out a handout that's almost identical to the quiz you're going to take. Probably tomorrow is where we're doing the first one. Probably Monday, unless I'm going to require everybody for Saturday school. It's going to take a unit circle quiz. I don't think I could. I could try. Cool. So, first thing that I want you guys to do is check for me is a protractor long enough to draw a straight line across this circle. Yard sale. So when you go skiing and stuff, you guys ever heard somebody say yard sale when somebody dropped something like this? Yeah. You know why? Not really. You ever been to a yard sale, garage sale? And it's just like crap laid out everywhere, right? When somebody has a really bad wreck and they're skiing or snowboarding, oftentimes like their backpacks open and stuff gets flung out everywhere. So that's where that terminology comes from. Somebody drops like a whole handful of stuff and it scatters everywhere. Yard sale. All right. Do you guys share protractors with each other? There might be some in your desks still. Cool. So interesting that you guys are already rolling without ever asking what we're doing with the protractor. But that's okay. So, check it out. I'm going to use a very similar circle. Yours is going to be more to scale, although actually Yeah, I can't save it over here. All right. Let me get a nice circle up here. Ba-da-doo. Oh my gosh, everything just going crazy here. What did I just do? All right, I'm going to get a quick circle because I didn't print an extra one for whatever reason. Okay, I'll give me a nice unit circle up here as well. And the only thing that's going to be different is I don't have marks on those points, but you guys do. And I'm just not going to take the time to get the marks on those points. But you guys do have them, at least in the first quadrant, right? Now, if we have the unit circle, and we do, what I want you to do is, do you see the 3 points in quadrant 1? Using your protractor, I'm going to get nice points up here. What I want you to do is connect from, and you're halfway. Oh, that could have been terrible. I want you to draw a straight line all the way through. So go through the center to the other side of the circle, and that's okay. You're just going to have to extend your lines. And then what I always do, and you'll see it, it's just my choice, it's up to you. I would leave a little blank along each of these, because we're going to write the degrees and the radians on there. So you don't have to erase it. I'll leave mine blank. Straight lines through. You're going to get them connecting all the way. Cool. And I probably should have given you a couple more points, but let's see here. We have a few ordered pairs. 1/2. There's one of them. Root 2 over 2. Get rid of that guy. Now, and now I have the same circle with just some different colors. Cool. I'm going to copy this one up here as well, and I'm going to take the numbers off. We don't need the numbers on it. Get out of there. Cool. What'd you guys learn in literature today? Still digital footprint? Nice. Is it super boring? All right. So you guys, I think at this point probably have these 3 lines. And I'm not choosing colors like intentionally from this point down to that point. Cool, cool. From this point down to this point. Double cool some more, and this point over here. Now, by doing this, we're building up this idea of the unit circle. And here's the part that's going to be a little bit challenging for you, but we're going to eyeball it. When I give you the unit circle, all these points will be here, just so you know. Yesterday, we took this piece and we looked at it really closely. Like, that's just me zoomed in, right? Now, as we go through, here's what I want us to think of. I know these angles that we turned at. I'm thinking you probably do because we wrote them yesterday. But here's my suggestion. I said that I like to write them in here. Do we want degrees or radians on the inside? Degrees. Okay. What was that first angle we dealt with? So 30 degrees. And that is so bold, I hate it. 30 degrees. Can you guys see that? I feel like I should have just made a bigger circle. All right, c'est la vie. Cool. So there's 30 degrees. What was the next one? 45 degrees. And the last one? 60. So I will, again, when you actually take the quiz, I'll have these there for you. Notice when I draw it to scale, mine are pretty varied. So I try to equally space them so it's easier to tell them apart. This isn't right though. These are all 30, I don't know, 30 divided by 4. These are all like 20 degrees, somewhere in there. Okay, this is the true scale of it. Now, we listed these points yesterday. What I want you to look at is in any of those points, do you notice a pattern? Like, as you go around the circle, maybe counterclockwise, do you notice a pattern in how those ordered pairs are written? So just a heads up, this is a good thing to see because that means people are thinking most of the time. Everybody looks up to their brain. I don't know, it's weird that we do that naturally. Maybe. You should probably be looking at your page though. Look for a pattern in this circle to see from your notes yesterday, is there a pattern with how these points are showing up? Any connections that you guys can see? I'll start. Every single denominator is what? Okay, there's a pattern that I recognize. Any others? So there's some opposite stuff happening, for sure, right? Like I see 30 degrees and 60 degrees, those points just flip. Okay, I thought this was Precalc, but I could be confused. It might even be you guys. I'm going to give us a countdown real quick until we start, until we kind of summarize it together. You guys tell me if this is an annoying countdown. 7, 6, 5. Somebody already hates it. I hate it. What's weird about what just happened?
7.
Who starts at 7? You could. It's just as loud as any other number. It's just not natural. If you're going to give me a countdown, you're going to start from, I'm guessing, one of 3 numbers. If you're about to launch a space shuttle, you might start at what? 10. Seems reasonable. Okay. What if you're, I'm trying to think of a situation where this makes sense. Give me another number you might start counting down from. 5 feels natural as well. I don't know why. As soon as I said I can't think of a single situation that it's like, we always use 5. I don't know, but it feels natural to me. There's one more. 3. That's way more common than any of the others, right? 3, 2, 1, go. Let's look at the x's. 3. Now they're square roots, but 3, 2, 1, and the x's, right? Okay. You will never see me write this again because I hate it, but I want you to think this. To make the pattern a little bit easier, is it still allowed? Square root of 1 is still 1. We just don't write root 1. Now, these triangles will always have these ratios between the sides. Here's where I want us to expand out. If I went one more, and with your straight edge, what I want you to do is try to go exactly horizontally. So over to this point on the circle. And I should have made a much bigger one. So there's a new point, and we're just going to go ahead and I'm going to draw that line there. First and foremost, do you think you can tell me what angle we're at? $120. Okay. Now, here's what I want you to think about. We're going to go ahead and add that 120 in, and this is on your worksheet, I assume. If you want to do it in your notes, you can. I just thought the circle would be a huge time saver. We're now at 120 degrees. Now, there are some ideas that we're going to formalize this later, but if I wanted bow ties and butterflies showing up, and I wanted to make that last little segment that I've drawn into a right triangle, where would I draw from this point? I would go straight downward. Now, the way that we've drawn this out, I don't want it to confuse you because there's a couple ways we can think about it. The 120 sits okay with everybody? Now, the 120 degrees, though, don't draw this one. I just want to make sure it's super clear. This is what you just told me was 120 degrees, that whole rotation. That means if I look at just the triangle, just this triangle that we're focusing on right now, what's this angle down here? Why 30? It has to be 60, right? And I see where your head's at, like I get it. This would be 60. What would this angle be? And then this one would have to be what? So notice, we get a 30, 60, 90 triangle with the 60 degrees as the interior angle here touching the center. You think it has something in common with this 30, 60, 90 of exact same size? They're congruent triangles, they just happen to be reflected. Which means, here's our big powers of deduction. To get to this point out here, what we saw is we had to go horizontally 1/2 and vertically root 3 over 2. That's how we got there. That's what that ordered pair means. That's what we did yesterday. What about to get to our new point? I go left the same horizontal distance. I think it's negative 1/2, right? Before we move on, does that part click? Cool. How high up did I have to go? root 3 over 2. Okay. Is the same thing going to happen on the next point? Now, on mine, I can like draw them, which is super convenient. You guys don't have that option because I forgot the graph part of it. But that point is going to live, oh, it's terrible. I'll start here. That point is now going to live here, right? And yours is much larger, I imagine. Cool. Without me talking about it, do you think you can tell me what point that's going to be? So that's the angle. I'm cool with that. How about the ordered pair at the end of it? Negative root 2 over 2 is the x, right? Because you went left, and then root 2 over 2. Now, just to make stuff a little bit simpler to talk about, I'm going to write these ordered pairs, but I just want to focus on the x's first. So I'll come back and do the y's in a minute. If I go one further, and I know it's not like the true perfect angle, but I need space to write. If I go, I will do it perfectly. It's just going to bug me. If I go to here, what is this x value going to be? All right. Now, looking only at the x's, we're just going to take a step further. I think that if I start at a number and ask you guys to count down, I just want to see if you can. I'm going to list a number, and I want you guys to count down. 3. Okay. Count back up. 1, 2, 3. Everybody here feel confident that you can do that? Could you do it again? Could you do it yeah, just a 3 up and down. You can do it, right? If you can do it, you're golden. Because check this out. If I'm just looking at the x's, this one was root 2 over 2, and this one was root 3 over 2. I just want to look at the x's, and I'm not going to deal with the quadrants, just the points on the circle. Now, they all have square roots, but it's not as nice if we have to say that. Everything's divided by 2, and we have square roots in every numerator. I know it doesn't look like it, but remember there is a square root of 1. Let's just count just to these points. 3, 2, 1. Negatives now. 1, 2, 3. 3, 2, 1, 1, 2, 3. What do you think is going to happen right down here? Is it 1 or 3? 3, 2, 1, 1, 2, 3. 3, 2, 1, 1, 2, 3. It just circles itself, going up by that amount the same every single time. Now, the part of the unit circle that always confuses people, not always, but one place where I see confusion, people get goofed up on whether you want to start with root 3 over 2 or 1/2. Like just getting that first point mixed up is where the confusion happens. This is going to seem like an easy question. The other one is 1/2, right? And can I call it root 1? And like if I'm looking at the numerator, I'm going to call it root 1, just so we can be consistent with the way we're thinking. Can you guys tell me what's bigger, 3 or 1? 3 is bigger. I'm pretty. Yeah, 3 is bigger. What's bigger then, root 3 or root 1? Let's do easier numbers. What's bigger, 4 or 9? So what's bigger, root 4 or root 9? Root 9. So that connection, it stays the same. If you add the square root to both of them, it still is true. If I asked this one, and this is the weirdest language for this whole thing, this point right here, it has an x and a y, right? What's bigger, the x or the y? And if I can remember that it always starts with root 3 over 2 and 1/2, even if I get the order mixed up, I know the x is the bigger of those two. What's bigger again, root 3 or 1? Root 3, so this better start at root 3 because it's further to the right. It's a bigger x value out of those two choices. Okay, for the y's, we see another nice piece. This was root 2 over 2, and this was 1/2. Looking only at the y direction now. And do you guys want a second to go around the circle to get all the x? Okay, I'll give you a second. Get all the x's. While you're doing that, I'm going to pull up my other quiz that maybe I should have just printed that one, but I thought this circle was nicer. And I've skipped some stuff, but I just want to highlight. The second that you have this one 30, 60, 90, this is a 30, 60, 90. 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 I get the same triangle showing up all over the place. Okay, notice, positives and negatives we have to be mindful of, but I'm just going to say the numbers. You finish counting for me. 3, 2, 1. Here's my 3, 2, 1, and then count back up.
1, 2, 3.
Okay, and we ended at 3. We better start at 3 again. 3,
2, 1.
and
1, 2, 3.
boom, you're done. The Y's, do they do anything different? Instead of starting at 3, only one little change. 1. But let's check just to see if this pattern's still there. 1, 2, 3. 3, 1, 1. It does the same thing over each part. The pattern is there. How do you remember, just in case you're a person who gets goofed up, what's the way that you remember which one is the X? Is this further right or further up? What's bigger, 3 or 1? The X better be the 3 here in this situation. Now, you'll notice something. That has hit these 3, these 3, these 3, these 3. We missed these ones. I did not talk about these points out here. Why is this 1, 0? Yeah, what circle are we on? So if I don't rise at all, I better go 1 over to here, right? If I don't run at all, I better go up to 1. If I don't rise again, I go left to -1 and down to -1. I just got every single point on the unit circle. And all I need is, realistically, I claim the first quadrant. All I need to remember is that the first number is √3, and everything else comes for free. Everything. Now, for the degrees part and the radians part, I have a way that I remember it. Do you guys? Like, as you think back to geometry last year, any idea how you get these angles? Go ahead. You add 15? 15 only works if you add to the middle one, though, right? Because 0 plus 15 is not 30. Like, there's an issue because you have to go back and forth, right? Now, I'm going to show you guys how I do it. I think I'll probably give you the degrees on the circle, just so you know. Now, is there a way to convert degrees to radians? Okay. Could I take the time to go, okay, 30 degrees. Do not write this. That's pi radians over 180 is our conversion, and that simplifies to 30 pi over 180, and this simplifies to 1 pi over 6. Could you do that? And then could you do it 11 more times? Do you love that idea? Now, other than the nice, perfect diagonals, skip the 45, skip the in-between angles here for me real quick. You just identify for me, if we skip these, and I can probably just get rid of it, I want to know what would you jump by. And this is how I remember it. Doesn't mean how you have to remember it. We're skipping that. We're skipping this. We're skipping this for now. And we're skipping this. Every remaining point on the circle is a jump by how much? 30. So if I didn't want to convert, like, and even if I just wanted to do it with degrees, I can just do 30 plus 30 is 60, is 90, is 120, is 150, is 180, and I can go the whole way through, right? Can everybody add 30 over and over? Okay, here's a huge challenge. 30 degrees, how many radians? Okay, so this sounds a little harder. We're going to do an easier one. Can you add 1/6 over and over? What's 1/6 plus 1/6? 2/6 plus 1/6. Plus, like 4/6, 5/6, 6/6, 7/6, so forth and so on, right? Check this out. One rotation of 30 degrees is the same as a rotation of pi 6 radians. Pi, and I'm going to have to do it here. And I'm going to get rid of all these on mine. I need a white pen. Make it bigger. We're going to get rid of all these. Just for now. All right. I know that the first angle is 30 degrees. Or how many radians? Okay, so there's part of this that I'm going to suggest we don't do it all in our head. You might elect to. Is that okay with me? Very much so. But check it out. 30 degrees means this first one, as long as they do that one conversion. Whether I physically do it or I remember it, it's 1 pi 6, right? If I turn another 30 degrees, it's just turning another how many radians? So what's pi 6, 1 pi 6 plus 1 pi 6. So somebody said it, I'm good with it. Do you agree with this though? 2 pi 6. That's the wrong spot though, isn't it? Because I meant to erase everything in the middle and then I got distracted. 1 pi 6 plus 1 pi 6 gives me to 2 pi 6. If I go one more, it's 3 pi 6. Here's 4, 5, and 6. Do you guys agree with that? Is that super hard to do? Is there anything about it that's annoying? I think it was Riley that gave me a different number than I wrote down, I think. Or I misheard. There's something that annoys me. I'm going to be much more specific. What's crazy annoying about this number? It should be simplified, in fact. Now, if you go through the first time adding all your pi 6, and here's 7 pi 6, and 8, and 9, and 10, and 11, and 12, right? I just haven't put them. But if you do this first, you get almost the entire circle. 2 pi 6 is what? Pi thirds. And this one, 3 pi over 6. Pi halves. 4 pi 6. 5 pi 6 does not simplify. Does this one? It's pi radians, which is what I'm expecting. We can get the whole unit circle, all the radians, just by being able to add 1/6 over and over. Almost. I missed all the middle angles because they're 15 away, right? But check it out, the same thought process. To get to that first 45-degree angle, that's how many radians? (45 out of 180), 1/4. Pi fourths. So check it out. I'm going to do this one on the outside just because my circle's a little smaller than yours. I know via one conversion that what is 45 degrees on my circle, when I multiply by pi over 180 degrees, I get pi fourths. Can you guys add by 1/4 repeatedly? Prove it. Let's check it out. Pi fourths. There's my first one. Go another 45 degrees. We're straight up. That's how many pi fourths? What would that simplify to? Oh, look, we already had it. Add another one. We're at 2 pi fourths. Add another one. 4 pi fourths. Gosh, that feels silly because it's pi. Hey, same, whoop, wrong thing, but same thing just happened. We're at 4 pi fourths. Add another one. 5 pi fourths. Add another one. And then this one, you could call it 8 pi fourths, or you could call it what? Now, weird, but it could also be 0, right? 0 degrees or 2 pi radian, or 0 radian, 2 pi radian, same angle. Okay. The whole unit circle comes from these patterns. Wherever you're at, you probably have a bit of it, or all of it maybe, I don't know, I can't tell. Tomorrow, Monday, we're going to take a quiz on it. You will get this. Not that. That. On a sheet of paper. I will give you the degrees. You are going to be expected to not convert radians 11, 16 times. Don't do that. Use the pattern. Don't work out every special right triangle. Use the pattern. Cool. For this evening or before then, what I would suggest, any Google of the unit circle will get you this and a million versions of this. You should try your best to finish that circle at some point before Monday. Okay. Now, I'm not going to go into it a ton more. I do just want to highlight real quick. Are the bow ties and butterflies present on this one? Kind of. They could be, right? The lines that you guys drew on your page when I first gave it to you were these. Like, those are the lines that were on your page. And then I just left off the other points unintentionally, but we got all these too. If you wanted your bow ties and butterflies, here they are. We get them all. Cool. Triangle here, if we're looking at that triangle. Or this triangle, and I'll switch color, here, if we're looking at that triangle. We get all of these pieces just given to us. Do I need to speak more about this right now? Okay. So, the neat thing about what we've just done is we've defined the entire unit circle without ever mentioning trig stuff. Like, it might feel kind of like we're doing some trig, and we are about to do some trig, but I would claim we haven't really done any trig yet. The fact that radians can be measured as radians, it could be geometry, it's general math, whatever you want to call it. We are going to take these ideas, and we're going to build up out from them. Cool. So, keep your worksheet. If it's not complete, you should complete it. But let's continue on. Now, the big idea here is we're going to link this unit circle to the idea of trigonometry, and that's where we will start today. So, I'm going to get my screen cleared of what we did today, just with this drawing stuff. And what I want you guys to do, the next section of this, the next subsection of this section, so this is still 4.2, but I think our bullet point yesterday, the main topic was the unit circle. We are just going to use our main topic today, expanding beyond that. Our main topic is these 6 trigonometric, or trig, functions. Cool. The 6 trig functions. When you guys learned about these for the very first time, I think you only learned there were 3. Sine, cosine, and tangent. And you probably weren't even taught that they were functions. You were taught that they were ratios of a triangle, relationships between the sides. And that's how they're defined, for sure. But if we can plug in an angle and it spits out a value, then it's a function, because that's what it does. It takes something and spits something out. So here we are, just checking these. We're going to write them once by name. What are the 3 standard that you guys know of? And I want you to write it exactly like I do. I'm going to switch the way I've always done it. What's the first trig function you think of? And maybe I won't switch it. Sine. Okay. Sine. This is the real name of it. Do we write sine when we're doing math? No. What's the shorthand? So I'll write out a little bit more. You guys, I'm not going to write this every time. Sine of angle theta is what this would be. Does anybody ever speak mathematics like this? What is the sine of angle theta? Maybe, now that I say it, it doesn't feel that weird. But it feels really weird to write it. This is the sine theta, or sine of theta if you want to be specific. Language-wise, we've seen it before, we'll see it again. This is a function. It is not just multiplication, which means I have a function sine, and what is the argument of this sine function? So you're absolutely right. That's a ratio that it gives me. It's the opposite in hypotenuse. You're thinking SOHCAHTOA. That's applicable. But when I say the argument of sine, it's the thing we're taking the sine of. It's theta. The argument of this sine function right here is theta. Okay. Now, if we want to, and you will see me do this constantly, if there's no ambiguity, which means it's perfectly clear, do I really need these parentheses? I will much more frequently write it like this. Just like when we did logs, how half the time there's parentheses and half the time there's not, it depends on if it's unclear. If I give you this one, and I don't want you to write it down, but I want to just make sure this issue is clear. What's the argument? Theta. What might somebody incorrectly call the argument? Theta plus 1. What could I do as a mathematician, human, whatever, to make it clear that I wanted the argument to be theta plus 1? In this situation, when it's not clear, this. If you ever see me write it without the parentheses, it will always be the only stuff that's connected to it. Okay. I'm not going to write all the other ones of angle theta, but we will write them. So we have sine theta. Cool. What's another one? Cosine. So here we go. Cosine. And it's called a co-function, just so you know. And I'm just going to say the same stuff happened there. What's the shorthand for cosine? Cos. You're never going to hear me say cos. It's cos. Or if you don't want the parentheses, I'm fine with it. Cos theta. One more. Tangent. Now, certainly related to the idea of tangents that we might see in other places, but this is also its own trig function. Shorthand for tangent? Tan. And if you want the argument in parentheses, but if there's only one thing in the argument, you do not need it. Tan theta. These are the three standard ones. Now, we're going to use that idea here in a moment of what you mentioned like a couple minutes ago, Barsega, with opposite and all that stuff. Like, that will show up. Do you know the other three that are hiding? I think we mentioned it yesterday. Somebody knew them. So, careful. I'm not asking what are the inverse functions, because those are arcsine, cosine, arctangent. Those are the inverses. We get three new ones. And I'm going to do this in a very particular order, and then we're going to generalize it one more time, because I always write my answers in the same way. Okay. We get sine, but we also get cosecant. And it's of an angle theta, so I'll just say, hey, look, same stuff when I'm not writing it. Anybody know what the shorthand for cosecant is? It can't be cos, because that'd be super misleading, right? CSC. And I'm going to keep doing this. I wish I hadn't, but we're already this far. So we get sine and cosecant. And that's like first of the list, first of the list. Okay. This feels odd, and I hate it that it worked out this way. Sine and cosecant match up. There's a sine and there's a what? So both are fine. There's a sine and a cosecant, but there's a sine and a cosine, right? A co-function, if you will. If there's a cosecant, what else do you think there is? A secant. S-E-C. Secant theta, not sec. Secant theta. Or, same thing with the argument. If you don't want it, don't include it. If it's clear. All right. One more. We got sine links with cosecant, and we'll see those connections as we work through the chapter. Cosine maps with secant, and I get secant in its cofunction. There's one more waiting. The cotangent. Cotangent. C-O-T. Not cot, cotangent. If you're caught saying cot, I'm never going to let it die. Although that's probably a lie, because I already apologized about language issues this morning. There's a T on the end of tangent. All right. So we've had these two ideas that we've looked at in this section already. And right now we've just maybe introduced some new words, maybe not. But we need to link them together. And traditionally the way that I've done it is I instead will say, hey, look at all these functions that we have, and let's see how these build up the unit circle. But we don't need the functions to build the unit circle. You can build the unit circle without ever mentioning any of these things, which is awesome. So, our big connection, and this is where we're going to leave off. Can I just use quadrant 1? Is anybody opposed to that? Like, because it's just going to repeat itself throughout. I would like to just do that. So, this last piece, and it's not its own section, let's join unit circle and trig. And I want you to sketch quadrant 1 of the unit circle for me, including the quadrantal angles. So all of quadrant 1, I'm going to cheat and get it on Desmos. You know, or here. Nope, I'll do Desmos. That's fine, because you're doing the same thing. Just quadrant 1. Just this part. This is all that I need. It is right here is what I'm going to copy and paste. I don't even need the numbers on it. I'll take them off. I'll change the contrast. Only want quadrant 1. And I'm always going to make my angles a little bit bigger than they really are because I like the space to write it. Okay. Here's quadrant 1 of the unit circle. Come on, be big. Big enough. Okay. Now, quadrant 1 is convenient because everything's positive. Something weird is happening here, and I don't know what it is. Get out of there. Do it right here. Okay. I'm going to use that one. And I lied because it's going to bug me. Why won't it move? The other day I got in a fight with my stuff, and it turns out that I had a book sitting here pushing a button is why my computer wouldn't react, and I fought with it for like 30 minutes, and I was so mad. Unplugging, replugging, never had to move the book. Okay, check it out. This is a part of the unit circle, which means I guarantee the radius is what? It's 1. Now, for this specific relationship, I want to pick any point on the unit circle. In our picture, it's quadrant 1 due to convenience, but it could be literally anywhere. Tell me if you think this is controversial. Versal. Any point on the unit circle can be represented as an ordered pair. Whether it's here or here or here, it doesn't matter. It can be an ordered pair, right? So, beyond that, I'm just going to arbitrarily pick this point, which I believe is 30 degrees, but I don't really care what it is. Check it out. This thing I know has a form x comma y, and you guys even know what it is. What's the ordered pair without looking in your notes? What's that first ordered pair right at 30 degrees? Root 3 over 2. Okay, that's all fine and dandy. I want to sketch this out just as a triangle, just on its own, and we're going to connect this right off the bat. Here's my theta for now. I know it's 30, but I'm just going to say it's theta for now. Okay, if we look at this, there is one name of a Lakota chief, if you're in my physics class, or a 3 words, SOHCAHTOA, sound familiar to, definitely physics. JV and Ken, do you remember SOHCAHTOA? Can you spell it for me? Okay, SOHCAHTOA. Okay, this is going to connect here. Now, we use this to represent what? S is for sine, and what's the OH? Opposite over hypotenuse. So we're going to do something real quick. Let's just call this any arbitrary point xy. It might be, I know it's root 3 over 2 and 1/2 in the unit circle, but for some angle theta, it's xy, right? Okay, I want us to think about what this triangle actually is. We have an angle theta, and if I wanted to think about what ordered pairs really tell me, can you tell me this vertical height? Because I need to, right? It's y. Okay. What about the horizontal distance? This part of it. That's the x, right? Okay. Let's just think a moment about the trig stuff. From this angle theta, I know 2 sides, and I know 3, but let's just pretend that I just knew these 2 for now. If I know this angle theta, I have that side and that side. Using O's and H's and A's, what sides do I have? That is what side? Opposite, adjacent, or hypotenuse? Opposite. And this is? And then just because this is what? And we are going to add it in now. I just want to make sure we have it. What's this radius if we're on the unit circle? So the radius is 1, right? Okay. Have I lost anybody yet? There's still an xy that represents it no matter what angle it is. Everybody cool with that? Okay. What is easier to do? Take y and divide it by some number x, or take y and divide it by 1? Everybody agree y divided by 1 is easier? Okay, so from this angle theta, I have opposite is y and hypotenuse is 1, right? Okay, you do not have to write all this, but I'll help you out with what we're actually writing. Opposite and hypotenuse. What trig function deals with opposite and hypotenuse? So do you agree that we obtain that the sine of theta, and you don't have to write this yet, is equal to, what's the opposite side length on this? And what's the hypotenuse? This feels unnecessarily clunky right now. Y over 1 just feels odd to write. I think we could simplify that. If I said what's sine over theta, nobody's going to read y over 1. You're going to tell me it's y. I want you to do the same thing for cosine for me real quick. Cosine of this theta, what would it be on this triangle using SOHCAHTOA? It'd be x for the adjacent, right, over 1. So if I said what's the cosine of theta, would anybody in here say x over 1? What would you say? Oh, check this out. All of a sudden, all these pieces get put together. And if you're not ready for it yet, you're going to have to be, because here we are. This xy is nice and it's fine. But we could represent this a different way. Instead of x, you guys just told me what is exactly equal to x. Try again. This is cosine of the angle that got us here. And this is y value, which we just said was what? The sine of the angle that got us there. We now have a way to calculate this out. There are so many shortcuts here that I can't wait to dig into. Check the unit circle that you have in front of you right now. Does it have all the radians and stuff in quadrant 1, I assume? Radians and points in quadrant 1. So check this out. If I asked you for the sine of 45 degrees, before anything else, are you thinking x or y for sine? The y value. If you go to 45 degrees, what is the y value of that ordered pair? Root 2 over 2. Sine of 45 degrees is root 2 over 2. Sine of pi fourths is root 2 over 2. I don't need to do any calculations. It's all on that circle. Give me one more. I want the cosine of 5 pi sixths. You can check your circle. You can do it in memory. The cosine of 5 pi sixths. I don't like root 3 over 2. You're close, though. I like your number. There's one part about it, unless you just were really quiet. Negative. The cosine of 5 pi 6 is negative root 3 over 2. All of your sines and cosines around the entire circle exist. We've highlighted the nicest ones. Okay. Now, to formalize this, I don't think I'm going to give you homework over the weekend other than study your unit circle. We could, but we're not going to. We're going to define these really quickly. So, eventually we're going to have like a huge sheet of stuff, which I will give you guys a big formula sheet so you don't have to write them all necessarily. But writing them once will be beneficial. Like, it helps. So, basic definitions. We're going to define 6 trig functions. Okay, now, these really and truly wind up as just ratios. I don't do this very often. I want you to write this exactly like I do. Okay, I always follow the same order. I want us to write the following. First, we'll just put a little preface. Given a circle of radius r, and a point on the circle. I'm going to say on, just like that. And we'll just say it's of the form xy. We have. Okay, and we'll be good for, I'm going to do the very first one. And then you guys do the unit circle and these other 5. And you'll see it over the weekend. You'll do it. Okay, check it out. When we're on the unit circle, what's the radius? Are there circles that radius isn't 1? So maybe instead of x over 1, cosine would have been x over r, right? Oh. Check it out. We are going to write sine of an angle theta. Directly under it, we're going to write cosine of an angle theta. And last, we'll do tangent of an angle theta. Sine was x or y? Y. Now, if it was 1, we just wrote y, but it could be y over r, right? Okay, this is irritating, and I get it. Next to sine, directly horizontal, after we do this, we're going to write the cosecant of theta. And you tell me if you can figure out how I got this. The cosecant is r over y. I'm guessing that everybody can tell. Next to cosine, I'm going to write secant theta. Next to tangent, I'm going to write cotangent. Every quiz, test, everything we do related to trig, this is how you're going to see the places to write your answers. This is x over r. What would secant be, do you think? And we're done. Boom. Finish tangent and cotangent. Unit circle quiz, 10 minutes, start a class Monday. Cool. No other homework other than study your unit circle. If you want a blank quiz, I'll go print some at lunch. Happy to give them to you. Cool.